Why are we obsessed with the number 13? Why does the number 17 make your skin crawl if you're an insect? Right now, beneath the dirt right under your feet, trillions of red-eyed, alien-like creatures are counting. They aren't counting seconds, and they aren't counting minutes. They are counting years. For over a decade, they sit in the pitch-black freezing dark, sucking on tree roots, waiting. They have no calendars. They have no clocks. Yet, with a precision that would make a Swiss watchmaker jealous, they will all wake up on the exact same night, dig their way to the surface, and flood the world in a deafening, screaming swarm. But here is the real mystery that baffled mathematicians for centuries. They only ever choose two very specific numbers. 13 or 17. Never 12. Never 15 or 16. Always 13 or 17. These insects discovered a deep, fundamental secret of the universe millions of years before humans figured out how to kindle fire. They are using advanced number theory to stay alive. They are the animal kingdom's ultimate mathematicians, and their survival depends entirely on a bizarre property of numbers that you probably forgot the moment you graduated high school. To understand why these bugs are mathematical geniuses, we first have to understand the terrifying horror movie they live in. Imagine being a species where literally everything wants to eat you. Birds, squirrels, spiders, snakes, fish, dogs, cats. If it has a mouth, it wants to crunch on a cicada. Cicadas are not fast. They are not venomous. They don't have stingers, and they taste like buttery asparagus to predators. They are essentially flying chicken nuggets. If they came out every single summer, predators would just wait for them. The bird populations would grow, the squirrel populations would explode, and the cicadas would be driven to total extinction in a few years. So, the cicadas adopted a radical strategy, numerical camouflage. They decided to stay underground for a very long time so that predators couldn't rely on them as a steady food source. If you only show up once every couple of decades, no predator can specialize in eating you. Their populations stay low and stable, and then suddenly, you flood the market. Trillions of you appear at once. The predators eat until they literally vomit, and yet, because there are so many billions of cicadas left over, the species survives. This is a strategy biologists call predator satiation. But why 13 and 17? Why not 10 years? This is where the pure mathematics comes in, and it revolves around a special class of numbers called prime numbers. As a quick refresher, a prime number is a number that can only be divided by 1 and itself. Think of numbers like 2, 3, 5, 7, 11, 13, 17, and so on. They are the atoms of the numerical world. They cannot be broken down into smaller equal pieces. Now, let's look at the numbers cicadas avoid. Let's look at a composite number, like 12. 12 is a highly divisible number. It can be divided by 2, 3, 4, and 6. Imagine you are a cicada brood, and you evolve to come out every 12 years. Now, imagine there is a predator in the forest, say, a species of wasp or a small rodent, whose population naturally cycles and spikes every 2 years. If the predator spikes every 2 years and you come out every 12 years, their spike will hit you perfectly. 12 is divisible by 2. What if the predator has a 3-year cycle? 12 is divisible by 3, so they will hit you again. What if they have a 4-year cycle? If you choose a cycle like 12 years, you are opening yourself up to an absolute mathematical slaughter. You will constantly intersect with the population peaks of almost every predator in the forest. You are mathematically doomed. Let's test this out with another number. What if the cicadas came out every 16 years? 16 is divisible by 2, 4, and 8. Any predator with a 2-year, 4-year, or 8-year life cycle will synchronize with the cicadas and have a massive feast, wiping them out. Now, let's look at what happens when a cicada brood chooses a prime number, like 13. Because 13 is a prime number, it rarely intersects with any other numerical cycle. Let's say a predator has a 2-year life cycle. How often will the 13-year cicada and the 2-year predator meet? To find out, you have to multiply the two numbers together. 13 times 2 is 26. They will only coincide once every 26 years. 13 times 3 is 39. They will only meet once every 39 years. By choosing a prime number, the cicadas ensure that even if a predator's population spikes, the chances of that spike happening at the exact same time the cicadas emerge are incredibly low. The predators simply cannot adapt to them. The predators cannot synchronize their own life cycles to match the cicadas because the math forces them apart for decades at a time. It gets even more mind-blowing when you look at the 17-year cicadas. If a predator has a 5-year life cycle, they will only coincide with the 17-year cicadas once every 85 years. For a predator with a short lifespan, 85 years is practically an eternity. Generations of that predator will live and die without ever seeing a single cicada, and then suddenly, out of nowhere, the forest explodes with food, but the predator isn't mathematically equipped to exploit it. But there is an even deeper level to this mathematical warfare, and it involves the cicadas competing against each other. There aren't just one type of periodical cicadas. There are multiple different groups, called broods, that emerge in different regions and different years. Sometimes, a 13-year brood and a 17-year brood live in areas that overlap. If these two different broods emerged at the same time too often, they would interbreed. If a 13-year cicada mates with a 17-year cicada, their offspring might end up with a mutated genetic clock. Maybe they come out in 14 years, or 15 years. As we already established, 14 and 15 are composite numbers, which means those hybrid offspring would be completely wiped out by predators. To keep their lineages pure and their cycles prime, the 13-year and 17-year cicadas need to avoid each other at all costs. And because they both chose prime numbers, the math protects them from each other. How often do 13 and 17 meet? To find the least common multiple of two prime numbers, you multiply them together. 13 times 17 is 221. That means a 13-year brood and a 17-year brood will only emerge in the exact same place at the exact same time once every 221 years. The last time this happened for the two largest broods in America, Brood 19 and Brood 13, was back in the year 1803, when Thomas Jefferson was the President of the United States. The next time it happened was the year 2024. It won't happen again until the year 2245. Think about the sheer elegance of that math. By using prime numbers, these insects have created a temporal shield that keeps them isolated from predators, and isolated from rival broods, allowing them to dominate the ecosystem for millions of years. But this raises a massive, burning question: how do they actually do it? An insect doesn't have a brain capable of doing long division. A cicada nymph resting in the dirt doesn't have a chalkboard where it's calculating the lowest common multiple of 17 and 5. They can't see the sun, they can't feel the winter snow, and they have no concept of a calendar year. So how do they count to 13 or 17 with such perfect accuracy? For a long time, scientists were baffled by this. They knew the insects were keeping track of time, but they didn't know what the internal clock was. The breakthrough came when researchers realized that cicadas are plugged directly into the heartbeat of the forest. Cicada nymphs live underground, but they aren't sleeping. They are active, tunneling through the soil and latching their straw-like mouths onto the roots of trees. They feed on xylem, which is the fluid that pumps nutrients from the tree's roots up to its leaves. Trees, of course, follow a strict annual rhythm. In the spring, when the weather warms up and leaves begin to grow, the fluid pumping through the roots becomes rich with amino acids and sugars. In the autumn and winter, when the leaves drop and the tree goes dormant, the fluid stops flowing, or its nutrient profile drops drastically. Every time the tree pushes a rush of nutrients through its roots, it's like a bell ringing underground. The cicadas hear that bell. 1 nutrient rush equals 1 year. To prove this theory, scientists conducted a brilliant and slightly cruel experiment. They took cicada nymphs that were tracking a 15-year cycle at the time and placed them into a controlled laboratory environment with peach trees. Under normal conditions, these trees would cycle once a year. But the scientists artificially manipulated the lights and temperatures to force the peach trees to blossom twice in a single year. The trees went through 2 full cycles of budding, leafing, and dropping within a 12-month period. The result? The cicadas miscounted. They registered the 2 fluid rushes as 2 separate years. They emerged a full year ahead of schedule, proving that they aren't tracking time through some internal digital clock. They are literally counting the pulses of the trees. But counting to 17 is still an extraordinary feat for a tiny insect brain. Try sitting in a dark room with absolutely no sensory input, no phone, no windows, and try to accurately count to 17 over the course of nearly 2 decades just by listening to a bell ring once every 12 months. If you miss a single count, you die. If you count too fast, you die. The evolutionary pressure required to perfect this counting mechanism is staggering. Millions of years ago, there were likely cicadas that came out at 7 years, 9 years, 11 years, or 15 years. Over vast stretches of time, natural selection brutally weeded out the bad mathematicians. The ones that came out on composite years were devoured into extinction. The ones that miscounted by a year or 2 were eliminated. Only the broods that possessed the flawless genetic programming to count precisely to 13 or 17 prime cycles managed to pass on their genes. What we are witnessing when a cicada brood emerges is the survival of the ultimate survivors, the winners of a multi-million-year mathematical elimination tournament. And when that countdown finally hits 0, the synchronization is nothing short of breathtaking. Within a matter of days, the ground becomes riddled with holes, looking like a giant piece of Swiss cheese. Trillions of nymphs claw their way out of the dirt, scale the nearest vertical surface, be it a tree trunk, a fence post, or a car tire, and begin a stunning transformation. Their hard outer shells split down the back, and they slowly crawl out as soft, white, winged adults. Within hours, their new exoskeletons harden, turning a dark, armored black, and their eyes flash a brilliant, demonic red. Then, the noise begins. Only the males sing, using special ribbed membranes on the sides of their bodies called tymbals. They flex and release these muscles at blistering speeds, turning their entire hollow abdomens into mini acoustic amplifiers. A single cicada can produce a sound louder than a lawnmower. When millions of them do it simultaneously in a single patch of woods, the noise can reach over 100 decibels. It is loud enough to cause permanent hearing damage to humans if you stand too close for too long. It is a literal wall of sound, a deafening, vibrating roar that completely overwhelms the senses of any predator trying to hunt them. For 4 to 6 weeks, the world belongs to them. They scream, they mate, they lay their eggs in the tender twigs of trees, and then, just as quickly as they arrived, they die. Their bodies rain down from the canopy, covering the forest floor in a thick, crunchy carpet of decaying matter. It looks like a tragedy, but it's actually a massive ecological gift. As those trillions of bodies decompose, they flood the soil with nitrogen and other essential nutrients, giving a massive health boost to the very trees that kept them alive for nearly 2 decades. It is a perfect, beautiful, cyclical feedback loop. Meanwhile, up in the twigs, the tiny eggs hatch. Microscopic, ant-like nymphs fall from the branches, drop onto the forest floor, and immediately begin digging. They burrow down into the cold, dark earth, deep below the frost line, away from the birds, away from the sun, away from the noise of the world. They find a root. They latch on. And then, the silence returns. The counter resets to 0. And in the deep, quiet dark, the grandest mathematical calculation in nature begins all over again. The story of the cicada forces us to look at the world around us in a completely different way. We often think of mathematics as a human invention, something we invented with symbols, algebra, and calculus to make sense of the chaos of the universe. We think of prime numbers as an abstract concept discovered by ancient Greek philosophers like Euclid. But the truth is, mathematics isn't a human invention at all. It is the underlying blueprint of reality. It is the language of nature. Long before humans ever drew a triangle in the sand, the laws of prime numbers were already dictating the laws of life and death in the forest. The cicadas didn't read a textbook, and they don't know what a prime number is called. But through the brutal, beautiful process of evolution, they became a living embodiment of the math itself. They carved the laws of number theory directly into their DNA. So, the next time you find yourself walking through a forest, take a look down at the soil beneath your boots. It might look completely still, quiet, and lifeless. But remember that right beneath your feet, thousands of tiny, red-eyed mathematicians are sitting in the dark, listening to the heartbeat of the trees, patiently counting their way toward the perfect number.